Imagine your phone lighting up one night with an alert from NASA. A planet has been found. It is close to Earth in size. Its temperature may allow liquid water, and it is near enough for astronomers to study. The first question around the world would be obvious. Is anything alive there? But even if NASA really finds a second Earth, we may still be unable to answer that question. That is the new race. We are not racing to meet aliens. We are racing to separate the signal of life from the tricks of nature. Under NASA's current schedule, the Nancy Grace Roman Space Telescope is set to leave Earth on August 30, 2026. Its name may not be as familiar as Hubble or James Webb, but Roman could permanently change the way we see the universe. NASA expects it to detect around 100,000 exoplanets by watching stars dim. It may find thousands more by using gravity itself. 100,000 new worlds. If just one of them truly resembles Earth, how much closer would we be to discovering that we are not alone? To answer that, you first need to understand how difficult planet hunting really is. A star can be overwhelmingly brighter than the planets orbiting it. Looking for one of those planets is like trying to see a firefly beside a searchlight from millions of miles away. So astronomers usually do not see the planet itself. They see its footprints. The first method is called a transit. When a planet passes in front of its star, the star dims by a tiny amount.
If that dip repeats on a regular schedule, scientists can estimate the planet's size and the length of its orbit. Roman will monitor roughly 100 million stars toward the crowded heart of the Milky Way. Instead of studying only a handful of targets at a time, it will capture enormous pieces of sky. Its main camera has a field of view at least 100 times larger than Hubble's, even though their primary mirrors are similar in size. That difference is crucial. Roman will not work like a detective following one suspect. It will work more like a city-wide security system, watching millions of possible events at once. The more stars you watch, the better your chances of catching something rare. But Roman has another method, and it is even stranger. It will use gravity as a magnifying glass. According to relativity, mass bends light. If one star moves almost perfectly in front of a more distant star, the gravity of the nearer star can briefly magnify the background light. This is called microlensing. If the nearer star has a planet, that planet can add a small extra ripple to the pattern of light. The alignment may happen only once. Some signals may last only a few hours. Miss one, and it may never return. That is why Roman needs to watch so many stars continuously. NASA expects the microlensing survey to reveal about 2,500 planets, including rocky worlds near and beyond the region where liquid water could exist. Some may even be rogue planets. Worlds with no sun, no sunrise, and no home star, drifting silently through the darkness between solar systems. But this is where science headlines can mislead us. Earth-sized does not mean Earth-like. Worlds with no sun, no sunrise, and no home star, drifting silently through the darkness between solar systems. But this is where science headlines can mislead us. Earth-sized does not mean Earth-like, and Earth-like does not mean inhabited. A planet could be close to Earth's size and still have an atmosphere thick enough to turn its surface into a furnace. It could orbit in the habitable zone and have no water at all. Or it could contain an ocean buried beneath miles of ice. Even the phrase habitable zone is only a first filter. It means the planet is at a distance where liquid water might be possible if the atmosphere and other conditions cooperate. Think of a house in a neighborhood with pleasant weather. Knowing the address does not tell you whether the house has running water, breathable air, or anyone living inside. Roman will help us find the addresses. Proving that something lives there requires another investigation. One of Roman's instruments is a coronagraph. It uses masks and shape-changing mirrors to block the overwhelming glare of a star and reveal the much fainter planet beside it.
The technology is expected to be 100 to 1,000 times more capable than previous space-based coronagraphs. But Roman will begin with large targets, worlds more like Jupiter. It will not take detailed pictures of tiny blue Earths with visible oceans and cities. Its real importance is proving that we can control starlight with extraordinary precision.
If Roman succeeds, that technology can help future telescopes directly study smaller planets orbiting stars like our Sun. Roman may not be the telescope that announces life. It may be the telescope that tells us exactly where the next telescope should look. And what will those telescopes search for? The answer is hidden in light. When starlight passes through a planet's atmosphere, different molecules absorb different colors. Astronomers split the light into a rainbow and read the pattern almost like a barcode. Water, oxygen, carbon dioxide, and methane each leave their own signatures. If oxygen and methane appear together in amounts that should not remain stable for long, something may be constantly replacing them. On Earth, life is one of the major forces doing that. But the universe is very good at producing false alarms. Oxygen can form without plants. Methane can come from geology. Water alone proves nothing about biology. A planet that looks alive in the first set of data may look completely lifeless after scientists understand its star, clouds, temperature, and chemistry. That is why NASA stresses that confirming a biosignature would require long observations, repeated follow-up, and several independent lines of evidence pointing toward the same answer. There is no single magic molecule that lets us shout, "We found aliens." And even if we detect life, it may not mean cities, spaceships, or an intelligence trying to contact us. It may be microbial. Yet one living cell on another world would still rank among the greatest discoveries in history. We know life began on Earth at least once. If it began independently on another planet, then life may not be an almost impossible accident. Given the right conditions, it may be an outcome the universe can repeat. But what if Roman surveys an enormous population of worlds, and the telescopes that follow still find no sign of life? That silence would also be an answer. It might mean Earth is far rarer than we thought, or the jump from chemistry to biology may be much harder than we imagine. The more apparently suitable planets we discover without finding life, the heavier the question becomes. Why does this world has forests, oceans, and people looking up at the stars, while the others remain silent? Roman's mission is therefore much bigger than adding names to a planet catalog. It can turn the search for life from guesswork based on a few unusual examples into a census of worlds across our galaxy. We will begin to learn whether solar systems like ours are normal or exceptional. How common are rocky planets? How often do worlds orbit at moderate temperatures? And how many planets have been thrown away by their own solar systems to wander alone? The answers will not arrive the night the rocket launches. Roman must travel, commission its instruments, and gather data over years. Real science is usually slower than a headline.
It is also more exciting because every answer has to survive attempts to prove it wrong. One day, your phone may light up with the announcement of the most Earth-like planet ever found. When that happens, do not ask only whether aliens live there. Ask what evidence we can see, what natural process could imitate it, and which telescope must look next. Because the discovery of a second Earth will not begin with a picture of a living creature. It will begin with a tiny change in light among 100 million stars. And that nearly invisible point may be the first hint that Earth was never the exception.